hello and welcome to our webinar, Single Pair Ethernet and Power over Data Line Reference Board. And also hello and welcome to Heinz, Adrian and Simon here. Hello guys. You do a lot of webinars recently and there are many people that know you, but maybe some of the ones who look right now don't know you, so maybe you can introduce yourself.
Yeah, should I start? Okay, my name is Heinz Senkner from Technical Marketing, and one of my main tasks is to develop reference designs which are, let's say, attractive for the market, where we can give our customers some value add. And we are in close contact with the customers, and I get the feedback what is necessary to develop. And then we go into new technologies, new designs, and this is one of the results then. So this is one of my main tasks.
Yeah, and I'm Adrian. I'm responsible for the German EMC labs. So I do a lot of customer support, helping the customer to pass the EMC test. Normally they come to me when they have EMC problems, then we try to find the solutions. So we are doing pre-compliance measurements. And during these pre-compliance measurements, you get a lot of ideas where the hurt of the customer is. So they have a lot of problems. And one big topic was always discussions about Ethernet, how to connect the Ethernet shield between shield ground and ground. And this is where we started with our first reference design. Remember the time when we discussed this a few years ago?
Mm-hmm. Yes.
So these were coming from this time and from our customer ideas, and now we are discussing the next design.
Cool.
And I'm Simon.
Mm-hmm.
I'm working in the product management, supporting the product manager, and in terms of simulation, measurements, and Single Pair Ethernet was one of my childs. I started 2018 around with during the norm standardization of IEEE 802.3. And it was like in this time, lots of customers are asking how to develop this. And I think this was good explained from Adrian, that it comes to the point that we need also some board, some device to explain it to the customer, to give the customer something on the hand, not only on paper.
Great. So we have hardware design, EMC, and the simulation here on the table. And also on the table are those two reference boards. One is the power source equipment and one is the powered device. And what I know is this is a media converter, so it's from single pair Ethernet to Ethernet, or a connection from Ethernet to USB, or from USB to single pair Ethernet. So in all the ways round, powered source equipment, the powered device. My first question is, what was your intention to make this board, and for whom is this interesting?
Yeah, some people ask me already, why is the single pair Ethernet so large, this board? Yeah, it has a background. The background is we don't get only the demand for hardware design for the single pair Ethernet, but also for other interfaces. And the aim was here to create a single pair Ethernet with power over Ethernet design. The two wires exchange of energy or transfer of energy and exchange of data. But we said, okay, for our customers, we can make more. We can integrate more interfaces, like here the 10 or 100 megabit Ethernet interface and the USB 3.1. And they can interchange data from each port to any other port, so that this design is made that way that they work individually and the customers can just pick out some of that components of interest. For example, the USB 3.1 interface, and can use it for any other application. So it's modular made and also modular layouted, modular on the schematics, that the customer can use any of these individual components and can use it for his design.
Yeah, and it's one of the reference design that is also EMC proved and tested. So we did a lot of testing, and I think we will discuss this also later, right?
Exactly, we do this. Just at the beginning, you mentioned one point, and this is what I also thought when I had these boards the first time, and this was the size. Yeah, when I think on single pair Ethernet, then I think on compact design, smaller than Ethernet especially. And when I look at these boards, I mean, they are not really big, but they are also not very small. So what was the reason that those boards are so, I would say middle big, yeah?
Yeah, complexity is the one thing. This is what I mentioned before. Complexity means a lot of controllers and components. Size is another thing, what you mentioned. I'm a little bit a burnt child with evaluation boards, which are very tiny, have 02, 01 components. If you want to learn, if you want to change something in the hardware design, if you want to adapt it to measure something, that tiny boards are very difficult to handle. So we said, okay, this is not a product which is in the end sold on the market for some dedicated application. That's a learning product for our customers. And there you need the possibility to change something, to solder, to measure. This is why we extended the size a little bit, that you can handle it easily on your workbench.
And also the filtering, right? Also needs some size, even for single pair Ethernet.
Yeah, this is also one main point of the board, because without filtering, then you get lots of noises, or you cannot separate data and power. And yeah, you mentioned it is big, but it was, in our case, we thought about it. We can reduce it in some way, only the data path, but then we will increase the size, the components for the power path. So you have to choose between each of them. And so this is one of the best solutions, I think, to have a balance between size and on cost, of course. And it is also easy to replace it. So if you want to change the components, it's also easy. You can do it by hand. So I think this is not a big problem for the developer to do this.
Okay, thank you. So as we are now on board level already in our discussion, does it make sense now to talk about the features of this board? Yeah, what are the features here?
Yeah, the features in general are that you have the possibility, starting at the power source equipment, to incouple some energy going to this interface, single pair interface to your powered device. The powered device gets the energy, the necessary energy, not more and not less, because you have the startup of this communication in the beginning and handling limitation of the energy between the PSE and the PD. And then you can have an individual powered device in the end, which gets energy and data, and you can transfer or to interchange to any other interfaces like the Ethernet or the USB 3. And I think this is a flexibility which you can't find easily on the market.
Maybe it makes sense that we explain the features on the screen. Yeah, I know you have prepared something, so maybe we can look at this graph here.
Yes, we can go a little bit more into the detail. This is the block diagram here, which you also can find in our reference design node on the internet. You can download the document. It is explained in detail. But let's have a short overview. This is the power source equipment here. And there are main two interfaces which are important to be explained first. The one is this single pair Ethernet with power, which is found here and which actually then divides the signal and the power path. So here you see the power connection, 24 volts from any external power supply going into that SPE+PoDL compliant controller here, which then sends the initialization to the PD and ramps up the power and is controlled here with this firmware given by the SDM controller here. And this is actually the main power part. Additionally, we have a switching controller here, which just supplies the 3.3 volts here, the controllers on this board here. The signal path itself here, once divided here by due to the interfaces, the magnetics here, to power and signal, we go to the phi. From the phi to the Ethernet bridge here, which goes on one hand here to the Ethernet connection or interface, and in the other hand here via additional magnetics to the Ethernet bridge here, where we go with the signal to the USB 3.1 interface. So you see again here the USB interface, the Ethernet interface, and the single pair interface. This was the idea, to have 3 of these components which can be used by our customers then individually. By the way, you will see that the signal transmission can be done vice versa from any port to any, so you can also send data from the Ethernet here to the USB and vice versa, or to the PD towards the single pair Ethernet cable here, which was the main application here. Okay, let's go to the other board. Let's go to the PD, powered device. We get the data and the energy from the power source equipment. The energy goes here into that PD controller. The PD, by the way, tells the PSE what kind of power category it has, and then it will ramp up the energy. And we have here again a switching controller, which then delivers the 3.3 volts to the other controllers, the signal controllers on this board. Once divided into power and signal, we go to via that signal path to the phi, to the Ethernet phi then, and then to the Ethernet bridge, where we have the Ethernet port here, 10 or 100 megabit, and go via magnetics then to the Ethernet and USB 3.1 interface. So again, we have 3 interfaces. This 2 here, the Ethernet and the USB interface, are same in the PSE and the PD. The magnetics are also the same, but the difference is here in that PD controller ramping up the energy. So this is quite similar, but in the single pair Ethernet path different.
So there's very much expertise in it. And as we are talking about features, one of the features is also that you did 2 application nodes. So why these 2 application nodes, and what interesting hardware developers or customers can find there?
Yeah, maybe I start with the answer. 2 application nodes, they have a different aim. The one is a reference design node. It's the RD041, RD041, which explains the hardware in detail. So each resistor can be found inside this document, is explained in detail. So also about the firmware, about the hardware design, the layout, the signal integrity, what is necessary to keep the EMC limits, and actually each controller explained in detail, so that you can download also the design files from the internet, which means you have the firmware inside, you have the Altium design package inside, you have the Gerber files inside, that you can reproduce these boards one-to-one, and you can use it by yourself. And each and every component is explained in this document. So this is the aim of this. That's some design description. The other thing is differently. This is an application node. This is the ANP 141. Which is Adrian's work, and I hand over to you. You can explain the details about this stuff.
Yeah, sure. In this application node, I talk about performance regarding EMC of our reference design. So we did a lot of testing. We did complete immunity testing, emission testing, and we get a lot of results. And in this application node, we show these results, and we show also the challenges that you have during EMC testing, of course. Since you have also a lot of auxiliary equipment causing challenging during EMC testing. And we will also compare shielded and unshielded single pair Ethernet cables.
Yes, this is a good point. By reading through this application note, I also came to the point where you compared shielded and unshielded cable. Maybe this is a question which is also interesting for developers. What is better, shielded or unshielded?
Yeah, this always depends. Like always in EMC world, it depends.
Okay.
So when we start with the continuous disturbances, immunity and emissions, it doesn't matter more or less. So we will have a very good performance in the emissions and immunity for the continuous immunity. So means conducted immunity and radiated immunity. We don't see a big difference when we use shielded or unshielded cable, so we can go up to, for example, 20 volts per meter in the radiated immunity for both type of cables. So there's not that big difference. But when we talk about transient immunity, we will see a difference. So with the unshielded cable, we have, of course, always the issue that a burst immunity or EFT immunity, for example, will reduce the data speed. And this is also what we discuss a lot. How do we more or less analyze the performance criteria on an interface? I think we discussed this a lot of times also with customers, how to more or less analyze if an interface is working as expected. A lot of customers using just a ping during the immunity testing, but of course that is not enough. A ping is only sending one data package per second. And so if something happens, you really don't see it. If you want to analyze an interface, you need to measure the speed and the error rate. Otherwise, you don't know what's happening. And especially for transient, let's say transient testing, bursts especially, you will have also the time between the burst packages where you may be able to send data. But when you send a burst, or when you test the burst package itself, you will get data corruption. So we need a continuous measurement, and this is what we do with the software. And then we see what's going on there. And so the conclusion for me is when we have a high transient immunity environment where we have a lot of transients, we need to take care that we maybe need a shielded cable, because otherwise we may lose some packages or get a reduction in the data speed. If this is acceptable, we can also use unshielded cables. If we want to have the complete high performance without data loss during a transient event, we should go for shielded cable.
So now this is clarified.
Maybe I explain this a little bit from the hardware point of view. Bursts and surge signals are transient signals, meaning they occur randomly, then they are there, and then they can, degrade the data transmission. They can impact it. And then the data speed and the bit will go down, and the bit error rate will increase. And this has to be tested, because this is a degradation of the performance and is in the EMC standards called performance criteria B. If it interrupts completely and doesn't ramp up anymore, it's C. This is in the most cases not allowed. But B is still acceptable. But how to test it? This isn't done with a ping. You must watch the data rate and the bit error rate. This we have implemented with some firmware and Windows program, Windows software, and you can watch this during the test. And this shows you then exactly if this change in cabling, in cable quality, in grounding design or whatsoever you like to have, if this is acceptable or not, because you can distinguish it. And this was the background of this firmware, to see really if there is a degradation or not, and can be watched precisely by that implemented firmware.
This sounds really, it's not an easy or fast answer on this question, on shielded or not shielded. Yeah. But I like this answer. I mean, if this is all inside application or this explanation, I think then it's interesting for everyone, no matter if he's a very experienced hardware engineer or not. When I also was reading through this application note, I could see that, especially on the bottom side of the board, there are a lot of diodes. Yeah, we have Schottky diodes, TVS diodes, also a gas discharge tube. Is this all necessary to have this on a board?
It definitely is, yes. It's not because to increase the turnover with some components. No, not at all. As I mentioned, the transients are signals with, for example, in case of surge, with a high energy. This energy occurs randomly, but must be the digital electronic must be protected against this. So if we have, in this case, 10 megabit single pair Ethernet, we have long cables. We have burst signals which may be incoupled here, and this must be then somehow handled. But they don't handle only the immunity point of view. We use, for example, the parasitic capacitances by these devices to filter against radiated emission on this board. So they have an aim not only for the transient immunity, but also for the radiated or conducted emission, where we say, okay, we use the best of these components. You can use disadvantages as advantages if you do it right in the design. So on first point of view is, sure, it is absolutely necessary that the board doesn't get damaged. This is the primary aim of these components. And secondly, you can use them also for the filtering of any kind of emission going out from this cable.
Thank you very much. Nice explanation. Now we have this single pair Ethernet plus PoDL boards. And in the past, years ago, we started with a gigabit Ethernet board. Then it was a gigabit Ethernet with power over Ethernet. We have 3 different designs now. So this is it? Or is there something coming more?
Yeah, actually, we watch the demand of the market and of our customers. When we started with the gigabit Ethernet, there was a high demand of it. Then after this, the single pair Ethernet was asked from industry, also from automotive industry, and we started with the 10 megabit because the development, we don't look in, let's say, in Google or something to find the design. We start from the scratch on, meaning we have a sheet of paper which is empty and we develop the design. So you can get the whole package of knowledge created by ourselves. So now the 10 megabits is established so far. And currently we work on the next step, which is the 100 megabit single pair Ethernet with power over Ethernet. We currently work on it. It will have a Wi-Fi port. This is a little bit more complicated and will most likely be on the market end of this year. And even this isn't the end. The next design then will be the gigabit single pair Ethernet. This is also already in the pipe, but will be something after the 100 megabit single pair Ethernet is on the market.
So everything gets faster. Everything maybe gets a little bit more complex.
Yes, it will. Yes, it will be more complex because we will keep the design that the customers can have several blocks. So it will be again a multi-purpose interface design where the customers really can pick out their blocks, what they need for their demand.
So this board, as we have it here, is complex as we discussed it. How was it for you to design it? Was it easy?
Yeah, actually, the well-known interfaces like USB or Ethernet we did before already. This was the easy part. But the single pair Ethernet, being something new on the market, you can't just Google something about it and then you can design it. No. It was quite complex. It was very complex. It took us a lot of time to guarantee the functionality, that the whole thing works like intended. And this was a real challenge in the beginning. But okay, once found, especially with the communication on the PSE side, it works, very reliable, passed all the functionality and EMC tests so that we can trust for having a good design.
Thank you very much, Heinz.
Yeah, and from the component side, like from choosing the right components for the design, especially for the power and for the signal part, it was also challenging to find the right values. Like I explained it a little bit before, to don't have a big coupled inductor and have a small signal transformer, but we choose this solution that we have a little bit bigger or a bigger single transformer with around 2 millihenry. But therefore we can reduce our coupled inductor to, here in this case, 400 microhenry or even smaller, so that we have an size and cost and perfect design for the customer. Yeah, and this was one of the challenges because during the time, lots of the standardization process, they changed a little bit, and this was a challenge for us to look again what we have to do, what we have to change. But now you see the results and it works very good.
Yeah, I noticed this design changed a lot. At the beginning, it was much more big in size, especially for the higher currents, right? With the smaller transformer, and now it's looking quite compact. Thank you very much, Heinz. Thank you very much, Adrian, and thank you very much, Simon, for having time today. Your answers were very interesting, and also thank you very much to all of you who watched this video. If you have questions, you can come to our website, check out for the application notes, or you can download our design files. And yeah, have a nice day and see you at the next webinar.